Production Engineering Crash Course. Welcome to the Production Engineering Crash Course. By the end of this course, you will have a strong grasp of the key concepts that drive oil and gas production and support safe and efficient operations. Throughout this course, we will explore production overview, flowing wells, artificial lifting, oil treating, oil storage and sale, saltwater disposal, and gas treating, giving you a solid foundation to understand how these systems work together in real field applications. The production stage is the most important stage in a well's life, during which oil and gas are produced. By this time, the oil rigs used to drill and complete the well have moved away from the wellbore, and the wellhead is usually outfitted with a collection of valves called a Christmas tree or production tree. These valves regulate pressure, control flow, and allow access to the wellbore in case further completion work is required. From the outlet valve of the production tree, the flow can be connected to a distribution network of pipelines and tanks to supply the product to refineries, natural gas compressor stations, or oil export terminals. As long as the pressure in the reservoir remains sufficiently high, the production tree is all that is required to produce the well. If the pressure declines and it is considered economically viable, an artificial lift method can be employed. Flowing wells are defined as wells that have sufficient reservoir pressure to cause oil or gas to flow naturally to the surface through the wellbore. These wells produce oil or gas without the use of any artificial lift methods. They require relatively little equipment or expense to bring hydrocarbons to the surface. The equipment commonly used consists of tubing, a wellhead, and a Christmas tree. Artificial lift is a technique used to bring oil from the reservoir to the surface when reservoir pressure decreases. It is generally achieved by using a mechanical device inside the well, such as a pump or velocity string, or by reducing the weight of the hydrostatic column through gas injection into the liquid at some depth in the well. Artificial lift is required when there is insufficient reservoir pressure to lift the produced fluids to the surface naturally. It is also often used in naturally flowing wells, which do not technically require it, to increase the production rate beyond what would occur naturally. There are currently four main common methods of artificial lift. 1. Beam pumping or rod lifting. 2. Electrical submersible pumping, ESP. 3. Gas lift. 4. Hydraulic pumping. Beam pumping. The pump is designed to be installed inside the tubing of a well, and its main purpose is to collect fluids from below and lift them to the surface. The most important components are the barrel, valves, traveling and fixed, and the piston. The pump is connected to the surface pumping unit by a string of sucker rods. The sucker rods are stroked up and down inside the tubing, activating the pump at the bottom of the well. At the surface, a large mechanical device called a beam pumping unit is installed. The beam pumping unit is essentially composed of 1. Engine or motor. 2. Gear reducer. 3. Crank arm. 4. Counterweight. 5. Pitman arm. 6. Walking beam. 7. Samson post. 8. Horse head. 9. Bridle. 10. Polished rod. 11. Stuffing box. 12. Sucker rods. 13. Tubing. 14. Casing. 15. Pump. Depending on the size of the pump, it generally produces 5 to 40 liters of liquid per stroke, often in the form of an emulsion of crude oil and water. Pump size is also determined by the depth and density of the oil to be produced, with deeper wells requiring more power to move the heavier lengths of sucker rods. Beam pumping offers several key advantages in field operations. First, it provides high system efficiency, making it a reliable and well-proven artificial lift method. It is also economical to repair and service, which helps reduce operating and maintenance costs over time. Another important advantage is its flexibility. Production can be easily adjusted by changing the stroke length or pumping speed. Finally, beam pumping systems have a high salvage value, both for the surface unit and the downhole equipment, which adds to their long-term economic benefit. Despite its benefits, beam pumping does have some limitations. It is generally restricted to relatively low production rates, typically less than 1,000 barrels per day. In addition, beam pumping is mainly limited to onshore applications, as it requires a large surface unit, which makes it impractical for offshore or space-constrained locations. Electrical submersible pumping, ESP. The electrical submersible pumping consists of an electric motor attached to a pump at the end of the tubing string. The electric motor drives a centrifugal pump, which forces oil from the bottom of the well up through the tubing and out at the surface. Electrical power is supplied through an electric cable attached to the side of the tubing and connected to the motor. Electrical submersible pumping offers several important advantages, especially in high-production applications. It has a high capacity for both volume and depth, making it well-suited for demanding wells. ESPs operate with high efficiency at production rates above 1,000 barrels per day, and generally require relatively low maintenance during operation. Another advantage is that minimal surface equipment is needed, which reduces surface footprint. In addition, ESP systems show high resistance to corrosive downhole environments and can be successfully applied in deviated wells as well as vertical wells with doglegs. Despite their advantages, electrical submersible pumps have some limitations. One key disadvantage is their poor ability to handle sand production, as the presence of sand can lead to increased wear, reduced efficiency, and premature equipment failure. Gas lift. Gas lift requires a source of gas and compression equipment. Proper installation and compatibility of gas lift equipment, both at the surface and in the wellbore, are essential for effective operation. To understand the principle of gas lift, it is necessary to be familiar with hydrostatic pressure and fluid gradient. Hydrostatic pressure is the pressure exerted by a vertical column of fluid, affected by the height and specific gravity of the fluid. Fluid gradient is the pressure exerted per foot of vertical height of the fluid column. The fluid gradient increases as the specific gravity increases. Gas lift works by reducing the specific gravity of the fluid. This diagram illustrates the basic components and flow paths of a gas lift system used in oil production. High-pressure gas, typically coming from a compressor or an available high-pressure gas source, is first cleaned in a scrubber to remove any liquids or solids. The gas then flows through regulators and measurement devices to control and monitor the injection rate. From there, the gas is injected down the well through the annulus and enters the tubing via gas lift valves installed at selected depths. These valves allow gas to mix with the produced fluids, reducing their density and helping lift them to the surface more efficiently. A packer is used to isolate zones and ensure proper gas distribution. At the surface, the produced fluids flow into a separator, where gas, oil, and liquids are separated. The produced gas can then be routed to low-pressure or high-pressure sales lines, sent to additional separation facilities, or flared if necessary. Liquids are directed to storage facilities or liquid dump systems for further handling. Overall, this system allows controlled gas injection, efficient production from wells that cannot flow naturally, and flexible operation across multiple wells connected to the same gas lift network. Gas lift offers several important advantages as an artificial lift method. It closely mimics the natural flow process of the well, making it an effective way to enhance or extend natural production. One of its main requirements is the availability of a reliable and economical source of pressurized gas, which makes gas lift especially attractive in fields where gas is readily available. Now, let's look at the disadvantages of gas lift. First, it's not feasible if there's no source of gas available. Second, the initial setup comes with a high capital cost. Third, it requires intensive maintenance. And finally, operating it can be quite challenging. Hydraulic pumping. High-pressure oil is pumped into the well through the tubing string. At the bottom of the well, the pressurized oil enters a mechanical device, causing it to reciprocate. This mechanical device activates a pump, which lifts oil from the producing formation along with the expended power fluid to the surface. The system consists of a surface power fluid system, a prime mover, a surface pump, and a downhole jet or pump. Power fluid from surface actuates the engine, which in turn drives the pump, and power fluid returns to the surface with the produced oil. Let's talk about the advantages of hydraulic pumping. First, it has no moving parts, which makes it simple and reliable. Second, it can handle high volumes of production without breaking a sweat. Third, a single package can serve multiple wells, which is super efficient. And finally, because of its design, the pumps require very little maintenance. Of course, hydraulic pumping isn't without its drawbacks. The upfront cost can be quite high, and operating the system is a bit complex, requiring trained personnel to keep everything running smoothly. Oil treating. Generally, the production from a well is a mixture of oil, water, gas, and sometimes sand. Foreign materials such as water and sand must be separated from the oil and gas before sale. This process is known as oil treating or oil dehydration, in which water is removed from the oil. The amount of this foreign material is referred to as the basic sediment and water, BSW. Normally, the BSW content must be less than 1% for the oil to be acceptable for sale. The basic types of equipment used for oil treating include separators, free water knockouts, and heater treaters. Separator. A separator is a large pressure vessel designed to separate production fluids into their constituent components of oil, gas, and water. Separator utilize the force of gravity to separate oil-gas mixtures, due to different densities of the fluids. The oil which is heavier than the gas falls to the bottom of the vessel and taken off through the fluid line. The lighter gas rises to the top and is removed for separate sale. Let's break down the major components of a separator. First, we have the primary separation section, where the bulk of gas and liquid are separated. Next is the secondary or gravity settling section, which further separates the fluids. Then comes the mist extractor, which removes tiny liquid droplets from the gas. The gas outlet lets the cleaned gas exit, while the liquid settling section ensures any remaining gas is removed from the liquid. Finally, the liquid outlet allows the separated liquid to flow out. Now let's look at the classification of separators based on their operating configuration. First, we have the horizontal separator, which can range from about 10 to 12 inches in diameter and 4 to 5 feet seam to seam, all the way up to 15 or 16 feet in diameter and 60 to 70 feet seam to seam. These are usually manufactured with either monotube or dual-tube shells. Next, the vertical separator varies from 10 to 12 inches in diameter and 4 to 5 feet S to S, up to 10 to 12 feet in diameter and 15 to 25 feet S to S. Finally, there's the spherical separator, which typically comes in diameters from 24 or 30 inches up to 66 to 72 inches. Next, let's classify separators based on their function. First, we have the two-phase separator, where gas is separated from the liquid, with the gas and liquid being discharged separately. Then there's the three-phase separator, which handles well fluid by separating it into gas, oil, and water, with all three fluids being discharged separately. Monotube horizontal separator. A monotube horizontal separator is a type of oil and gas pressure vessel designed to separate production fluids, specifically oil, gas, and water, into their individual components. It consists of a single cylindrical shell, a monotube, oriented horizontally, typically used in upstream oil production, particularly for high gas-oil ratio GOR wells or foamy crude. Monotube horizontal separator key characteristics. Design: a single large horizontal vessel, compared to a dual tube which has two barrels. Separation method: uses gravity to settle liquids and, with internal baffles, allows gas to separate from the liquid surface. Operation: inlets, outlets, and mist extractors are arranged to maximize gas-liquid separation in a horizontal flow path. Size: varies significantly, from 10 to 16 inches in diameter and 4 to 5 feet long to up to 15 to 16 feet in diameter and 60 to 70 feet in length. Let's talk about the monotube horizontal separator and why it stands out. First, higher capacity and efficiency. Monotube units usually offer a bigger gas flow area and a larger liquid-gas interface than dual-tube separators at a similar cost. That means they can handle more, faster. Next, retention time. With their larger single-tube volume, these separators give liquids more time to settle, improving the separation process. Then, there's ease of maintenance. Cleaning monotube units is straightforward, much simpler than dealing with dual-tube designs. They also perform better in cold climates. The design allows better contact between liquid and the warm gas stream, so they're less likely to freeze. Finally, space management. Their low profile makes them perfect for stacking on offshore platforms where every square meter counts. All in all, monotube horizontal separators combine efficiency, reliability, and smart design. Let's look at where monotube horizontal separators really shine. They're perfect for high gas-to-oil ratio wells, handling both high and medium ratios with ease. They're also excellent for foaming crudes, thanks to that large liquid surface area which keeps things under control. When it comes to three-phase service, monotube separators can efficiently separate oil, gas, and water all in one unit. And in well testing, they're a go-to choice, widely used across oil and gas production facilities for reliable, accurate results. In short, whether it's tough fluids or complex mixtures, these separators handle it smoothly and efficiently. Now, let's talk about some operational considerations for monotube horizontal separators. First, liquid level control. Since the surge space for liquid is limited, careful placement of the liquid level control is crucial, more so than in vertical separators. Next, installation. These units are easier to skid mount, which makes them a favorite for quick field connections. And how do they compare to vertical separators? Well, vertical separators do handle surges, or slugs, a bit better. But when it comes to high liquid capacities, horizontal separators really take the lead. In short, a bit of planning goes a long way, and with the right setup, these separators are highly efficient and flexible. Dual-tube horizontal separator. The dual-tube horizontal separator, also known as a double-barrel separator. This is a type of industrial pressure vessel commonly used in the oil and gas industry to efficiently separate well fluids into gas, oil, and water. What sets it apart is its design for high liquid capacity, making it ideal when large volumes of fluid need to be handled reliably. Now, let's explore the key characteristics of a dual-tube horizontal separator. In terms of design, it features two cylindrical shell sections, one stacked above the other, connected by pipes to work as a single system. As for operation, the incoming fluid first enters the upper tube, where bulk separation begins. Baffles help drain free liquids immediately into the lower section, while gas moves straight through the upper tube at higher velocities. This clever design allows the separator to handle high liquid capacities efficiently, keeping the flow smooth and reliable. Dual-tube horizontal separator offers several important advantages. First, high liquid capacity. This configuration allows for much higher liquid capacities compared to single-tube designs. Next, reduced re-entrainment. The liquid portion is isolated in the lower tube, which reduces the risk of liquid disruption and re-entrainment of any liquids back into the gas stream. And finally, ease of installation. Like other horizontal separators, they are typically easier to skid mount, service, and require less piping for field connections. Altogether, this design is highly efficient, reliable, and practical for demanding oil and gas operations. Primary applications. Dual-tube horizontal separators are used in the oil and gas industry in conditions where a standard horizontal separator's advantages are needed, but with the added requirement of high liquid throughput. High gas-oil ratio streams. They are particularly suitable for processing large volumes of gas while managing significant liquid loads. Well testing. These are commonly used for well testing operations. Three-phase separation. The design can be adapted with internal baffling or interface liquid level controls for three-phase separation, oil, water, and gas. Vertical separator. A vertical separator is a type of industrial pressure vessel, oriented with its cylindrical axis perpendicular to the ground, used to separate a multi-phase fluid stream, oil, gas, water, and solids, into its individual components based on their density differences. It is commonly used in the oil and gas industry, especially in applications where ground space is limited. Vertical separators have key characteristics. In terms of functionality, they act as scrubbers, knockouts, or treaters to remove liquids from gas streams. In terms of applications, they are preferred for offshore platforms due to their small footprint. As for design, the gas leaves from the top, while liquid is removed from the bottom, typically through a dump valve. Finally, the vertical separators types are available in two-phase, gas and liquid, and three-phase, gas, oil and water configurations. How does vertical separator works? The separation process in a vertical separator relies primarily on gravity. The incoming fluid mixture enters the vessel through an inlet, typically a side nozzle, and hits an internal inlet diverter. This causes a sudden change in momentum, facilitating the initial separation of the bulk liquid and gas phases. Gravity settling. Due to differing specific gravities, the heaviest components, water, then oil, fall to the bottom of the vessel, while the lighter gas rises to the top. Liquid collection. The bottom section of the vessel provides retention time for the accumulated liquid, allowing smaller gas bubbles to escape and rise to the vapor space. Gas polishing. As the gas flows upward, it passes through a mist extractor, a mesh pad or vane pack, near the top outlet. This component captures fine liquid droplets that were entrained in the gas stream, ensuring the exiting gas is clean and dry. Outlets and controls. Separated liquids, oil and/or water, are removed from the bottom via dump valves controlled by liquid level controllers. The gas exits from the top via a pressure control valve. Vertical separator advantages and applications. Small footprint. It occupies less floor space, making it ideal for use in space-limited areas like offshore platforms. Handles slugs and sand. It can handle intermittent slugs, sudden surges, of liquid more effectively and are well suited for processing well streams with high sand or mud content, as the solids can be easily removed from the bottom. Stable liquid level control. The large vertical distance between the liquid level and the gas outlet makes the liquid level control less critical and helps prevent liquid carryover into the gas line. Effective for high gas-liquid ratios. It generally handles high gas volume fractions, low to moderate liquid content, very well, making it suitable for applications like gas scrubbers. Spherical separator. A spherical separator is a compact, ball-shaped pressure vessel used in oil and gas production to separate gas, liquid, and solids, especially sand, from well fluids. Renowned for high pressure resistance and a small footprint, it is ideal for offshore platforms and crowded, temporary, or remote installations. How does spherical separator works? The spherical design relies on gravity and velocity changes to separate incoming well fluids, gas, oil, water, and solids. The spherical shape inherently handles high pressure and reduces structural stresses effectively. Inlet diversion. The fluid stream enters and hits an internal baffle, causing a sudden change in direction and momentum, which forces liquids and solids to the bottom due to inertia and gravity. Gravity settling. The spherical space allows different density components to segregate, with the heaviest materials, sand and water, settling at the bottom, and gas rising to the top. Gas polishing. Gas flows upward through a mist extractor, such as a wire mesh pad, to remove fine liquid droplets before exiting the top of the vessel. Outlets and controls. Liquid levels are managed by control systems and dump valves at the bottom, while gas pressure is controlled at the top outlet. Moving on to spherical separators' key advantages. Their compact and portable design makes them perfect for areas with limited space, such as offshore rigs or crowded processing facilities. The spherical shape also provides superior pressure resistance, giving them excellent structural integrity for high-pressure operations. They are highly efficient at removing solids from both liquids and gases, and perform particularly well when handling foamy liquids or slugs. On top of that, maintenance is minimal, as these units usually don't rely on complex internal filters, which helps reduce downtime and keep operations running smoothly. Of course, spherical separators do have some limitations. Their liquid surge capacity is lower compared to horizontal separators, so they aren't ideal for handling very high liquid volumes. Additionally, they require periodic maintenance to prevent solids from building up at the bottom, ensuring continued efficient operation. In terms of applications, spherical separators are incredibly versatile. Their compactness and portability make them easy to transport and install, especially on offshore platforms or for temporary testing setups. The spherical design also gives them excellent pressure handling capabilities, making them well suited for high-pressure operations. Certain designs, called spherical sand separators, are highly effective at removing sand and other heavy solids from well fluids, protecting downstream equipment from damage. You'll often see them used in subsea production, artificial lift systems like ESPs and PCPs, and during well testing phases, where their compact, efficient design really shines. Free water knockout. A free water knockout, or FWKO, is used to separate oil, water, and gas from well fluids. The mixture enters the vessel through an inlet valve and is allowed to slow down in a large settling chamber. This gives the liquids time to separate naturally. Free water settles at the bottom, oil is removed through a separate outlet, and gas rises to the top, where it's extracted through a third outlet. This simple yet effective process ensures clean separation and protects downstream equipment, making FWKOs a reliable component in oil and gas production. In principle, a free water knockout is almost identical to a separator. The vessel is called a free water knockout because it is designed to remove only free water, not water that is emulsified with the oil. The oil and water outlets are controlled by level-controlled valves, which prevent the vessel from draining completely and maintain a gas cap at the top of the vessel. Free water knockouts are commonly used for low-pressure wells and can handle high fluid volumes. Heater treater. Also called an emulsion treater, it is used to separate oil-water emulsions. It is similar to a free water knockout, but the treater includes heating capability through the use of fire tubes. Combustion of gas within the fire tubes is used to heat the oil-water emulsion, aiding separation. As the oil-water mixture heats up, the emulsion breaks, separating into clean oil and clean water. The water is removed from the bottom of the vessel and sent to the water disposal system. The clean oil is withdrawn from the center of the vessel and sent to oil storage tanks for sale. Any natural gas present in the oil-water emulsion exits from the top of the heater treater. A typical combination of oil treating equipment is shown below. Oil, water, and gas are produced as a mixture and sent to a free water knockout. The remaining oil-water emulsion leaves the free water knockout and is transferred to the heater treater. On offshore platforms, a high-pressure separator is often used instead of a free water knockout. Oil storage and sale. At a typical facility, sufficient storage is provided to accommodate oil from 2 to 3 days of production. Oil may be withdrawn from the tank and sold by truck, tanker, or through a pipeline to a refinery. A lease automatic custody transfer (LACT) system measures the volume of oil as it passes into the pipeline and also monitors the BSW content. Offshore production platforms may be equipped with oil storage facilities if located in shallow water. The clean oil can then be sold through a pipeline running from the platform along the seafloor to the shore. In deep-water operations, oil is transported through a pipeline along the seafloor to a storage platform in shallow water. Sometimes, a storage platform is not necessary, and the oil is shipped directly into the sales pipeline. For remote oil fields, deep-water locations, or small oil fields where seabed pipelines are not cost-effective, using an FPSO, floating production, storage, and offloading unit, is a good option. Oil is stored in the FPSO and later offloaded onto tankers. Saltwater disposal. To prevent environmental pollution, produced water must be re-injected into the ground, often into the same reservoir from which it was extracted. The water is collected from the oil processing equipment and usually stored in a tank until a sufficient volume has accumulated. In offshore operations, salt water from the wells can sometimes be discharged into the sea. However, the water must first pass through several treatment devices to remove any traces of oil. Gas treating. Natural gas consists of various components present in different concentrations, including water and other impurities. Reasons for treating natural gas. First, to meet sales specifications and customer requirements. Second, to recover valuable byproducts, such as CO2 and elemental sulfur from H2S, which can fetch a higher price if marketed separately. And third, to facilitate safe transmission and prevent hydrate formation. Gas sweetening is the most common gas treating process, also known as amine gas treating or acid gas removal. The process consists of two main units, the absorber and the regenerator. In the absorber, an amine solution removes H2S and CO2 from the upflowing sour gas, producing a sweetened gas, H2S free, and an amine solution rich in absorbed acid gases. The rich amine is then routed to the regenerator, a stripper with a reboiler, to produce regenerated or lean amine, which is recycled back to the absorber for reuse. The sweet gas normally goes on to additional processing such as dehydration and hydrocarbon recovery. The acid gas contains most of the CO2 and sulfur compounds, is either flared or sent to a closed sulfur recovery unit. Thanks so much for watching. That wraps up today's presentation. If you enjoyed it, don't forget to like and subscribe. It really helps us keep creating more content like this. See you in the next video.